In the last episodes, we have learned about deferred actions and how they can be used to reduce locking and prevent deadlocks. Can we implement deferred actions using C++ coroutines? I'm Sonia. You're welcome to C++ versus Rust, where you will learn how to implement deferred actions in C++ using coroutines. Once again, welcome. This is C++ versus Rust, where we will learn how to implement deferred actions utilizing C++ coroutines. From the last episode, you may remember we have asked a question. How do I implement a method such as process forwards, which will lock the output pin, and then under this lock it will call propagate forwards? How do I get this propagate forwards return to me a deferred action so that the lock will be gone when I execute this deferred action from the main scope of the program? The problem with coroutines is that if I was awaiting here for some code to be executed, this await would happen within this lock. So even if my execution was suspended here, when it's resumed, I'm under the lock, because the state of a lock is stored in the stack of the coroutine. So how do I do that? So that I can return this deferred action which contains the coroutine, but we escape that lock. How can we escape this lock? Let's look at process backwards function of the target node. What we don't like about process backwards in particular is that it creates this sequential deferred action where it consists of multiple deferred actions, and the reason is that the first deferred action returns more deferred actions to be run after this first deferred action and before the next deferred action. So this is essentially an await. This sequential deferred action could be replaced with a coroutine which awaits for this propagate backwards. But we're doing this under the lock. Can we make it so that we await for this propagate backwards, but without this lock? Right? Can we do that? So when we process backwards from the target node, we lock the input pin of that node. And the reason is that we have to read the connected pin. And once we have that connected pin, the read lock on this input pin of the target node is no longer needed. Now we can use this connected pin and ask it to give us owning node and call process backwards on that node. So that will give us deferred actions, and then we return those deferred actions to the user. But transfer node has returned to us two deferred actions. One of those deferred actions was to do this, to go to the input pin of the target node, get the connected pin, and call process backwards on the transfer node in this case. And this returned us a new deferred action. But where does this deferred action go? This deferred action, it will be executed after this deferred action, but before this deferred action. So once this deferred action is executed, after that we have to execute this one. The pattern looks very similar to asynchronous programming. It appears that the code of this action executes and then it awaits the code of this action, and after await it resumes and it executes with this action. So perhaps we can replace those lambdas, those actions. Maybe we can replace this whole sequential deferred action with one coroutine which will await for this code. Can we do that? So when we're invoking connected pin and guarded pointer owning node process backwards, we remember propagate backwards. We call this under the read lock for this pin, for this input pin. So we're still holding the read lock on input pin when we're calling this method. But process backwards on the transfer node returns a deferred action, so it doesn't execute this code here or here under that lock that we're holding. This will be deferred for later when we release the lock. So What we can do, I think, is create a deferred coroutine. Because just look at it. This is a piece of code which is split into two parts. It's sequential. It's a deferred sequential action. If it's sequential, it's the same as coroutine, right? Coroutines are sequential. And there is this point here of await. So we did something, and after that, we will be awaiting for more actions. And after we finish awaiting, we'll do this. So how about we convert this sequential into a coroutine? Let's do that. This is a process backwards method of the transfer node in our new example. We're using here a deferred coroutine. What is a deferred coroutine? A deferred coroutine is a helper function which returns an action but takes a coroutine as a parameter. What is coroutine? This is a coroutine class. It extends a coroutine handle specialized for our promise class. We use our promise class as a promise type. This is our promise class. So when we define this function, compiler will look into promise type of the return type of this function. So it is a pretty interesting construct. This function body is essentially a promise, and when we call it, we obtain a coroutine, created for us by calling getReturnObject on our promise type. Okay, so we got the coroutine object. What can we do with a coroutine object? The coroutine object has a next method. This is our method, we defined it. And it takes execution policy. We have upgraded execution policy to also handle coroutines. Coroutine next method is responsible for poking the coroutine. It calls resume on inherited coroutine handle, and that pokes the coroutine. It makes the coroutine continue from the saved location. And then, from this next method, we return whether the coroutine has finished or not. So why would the coroutine suspend its execution? Let's look at the promise. The promise defines initial suspend as suspend always. This means that coroutine is always created in the suspended state. We also have final suspend, which means that the coroutine is suspended before finishing. So these are our explicit suspension points. So this is our promise. When it gets turned into coroutine, we have current location saved in that coroutine handle. And it is suspended coroutine. When we resume it, it will run instructions from that location. We can see we will log debug message. We'll call propagate backwards on the input pin under the read log. It will give us back an action. We check if we have received an action. And we await on that action. Wait a second, how are we awaiting on this action? It's action, not coroutine. How can we be awaiting on action? As it turns out, in C++, you can co-await on anything. For example, you can co-await on an integer. You can co-await on absolutely anything you like. How is that possible? It's possible because your promise can implement await transform. And await transform can take whatever parameter you please. In our case, it takes an action. And I'm storing this action in the promise. In the private field, mNext. So by doing co-await on propagate, which is an action, I'm suspending this coroutine, and at the same time, I'm sending this action that I received here from propagate backwards to my promise. It becomes this mNext field. Alright, so who's going to execute that now? Let's look again at our next method of the coroutine. We have a line here which says get the promise from the coroutine handle and call the next method on it, forwarding the execution policy. So we have this policy and we're forwarding it to the next method of our promise. Let's see how that works. This is the next method of our promise. It takes the execution policy. First we check if there was an exception. If there was an exception, we rethrow it. So if exception happened in the coroutine, we forward it to a calling context. If there is no value in them next, we just return that there is nothing next to do. if the value happens to be a coroutine, we call next on that coroutine, and we forward policy to it. So if that action that we stored was a coroutine, we keep poking it here from this promise, from this parent coroutine, until that coroutine is done. And when it's done, we set next to nothing, and we return false. And when we return false, then from this if statement, in the next method of the coroutine, we now jump to resume. So we resume our coroutine that was awaiting on that action. This means that this co-wait is ready, and now we resume this coroutine. We continue with this instruction now until the end, and we finish this coroutine. And this will say, yes, I'm done. So if we're co-waiting on an action that is a coroutine, then it will be a child coroutine that will be poking here in the calls to next. But if it is not a coroutine, we just call run actions, and we execute those actions synchronously. So now process backwards method returns just one deferred coroutine, which is easy to read, instead of deferred sequential with 2 steps. I think we can agree that deferred parallel is easy to read each of the parallel actions. We know it's parallel. We don't need to connect them into our brains as one flow, as here. So in here, we need to connect this with this, understanding that this will happen in between. So that's not amazing for our comprehension. But for the deferred parallel, these 2 deferred actions are parallel, and we understand that there is no relationship between them. So it's easy to understand what's happening in this situation. So coroutines are fixing the sequential actions, where there is a breaking point, where we need to jump out of the current function and then come back. So we're gonna jump out and come back. And it is a deferred coroutine, so that we wrap this coroutine into an action that we return, so that if I propagate backwards is called when we hold some lock. We're not executing this coroutine yet. We're just returning an action that contains it, and we'll execute this coroutine later. So we have all the benefits of deferred actions, and we have all the benefits of the coroutines. Now, another question one can ask, what if our nodes were doing some I/O, and maybe we would like to use some asynchronous I/O? That's a good question. This isn't a part of this design. However, you can imagine that we can implement another policy. This policy controls how actions are executed. It doesn't only control the coroutines, it controls actions that are executed. So the policy could also have a mechanism to check the I/O. While we're executing actions, we can just check the I/O. Whether it is a coroutine or not, we can still do that. So we can have fully asynchronous I/O, whether your code is using coroutines or not. But this standard policy implementation is just for CPU-bound tasks. So you can execute actions sequentially or in parallel, or it can be a coroutine and it's like sequential action. So you execute steps of the coroutine one after another. Alright, so these are deferred coroutines. Let's check if they actually work, because they look pretty. You can see Visual Studio Code doesn't highlight anything in red. It seems like everything is syntax correct. Things make sense, but do they work? Does it work the way it's expected? Let's check that. Let's build our example. Let's run it. Okay, we can see that everything looks good, right? 7 times 9, 63. 7 divided by 9, 0.777. Right? 11 times 5, 55. 11 divided by 5, 2.2. Process backwards. So this is test 10. So this is our new example in parallel execution. So we're actually running some of those coroutines in some parallel threads. The sequential, same as deferred sequential. If we get deferred action for target node U and deferred action for target node V, this will run on one thread and this will run on another thread. So we have 2 parallel, branches. You have 2 branches executed in parallel. And we know that propagate backwards is using a coroutine, same as here. So we have achieved a mix of parallelism, coroutines, and deferred actions all in one solution. And we can have coroutines mixed with synchronous functions all in one bucket. Isn't it just amazing? So this is C++, right? Let's check the log to see how this worked. So we will look into sequential execution of our example. So you can see we load the value from the source, we lock, unlock. So this is where we put the value on the output pin of the source node. Here. And then we see process backwards from the target node. Here. Invoked as a deferred action. That is because we called process backwards inside deferred action of deferred parallel. So we call process backwards. And this is the whole call. And after that, we have a deferred action. So this deferred coroutine was returned from process backwards. And this is what happens inside this coroutine. The reason is because we co-await. So this context leaves all time from the beginning to the end. It leaves all that time. So whatever we define in this context will live until the last line of this coroutine. So for example, this propagate variable we defined here will have a lifetime of this whole coroutine. It will survive the suspension point, because this is how coroutines work. So we acquire the read lock on the input pin, and we call propagate backwards, but the lifetime of this lock is only this single line of code. This lock will not survive until this co-await. We can see it here. We're locking 36 tulips, which is the input pin of the target node U. We're getting the connected pin, the owning node, which is the transfer node, and we call process backwards on the transfer node. But that process backwards returns a deferred action. We can see this is process backwards of the transfer node, and it returns deferred coroutine. So this coroutine will not be executed. It will just be returned. And then we see we unlock 36 tulips, which is an input pin of the target node U. So at this line, we don't have that lock anymore. And we can co-wait on those actions returned by transfer node. The next thing that we can see is we invoke that deferred coroutine that we got from transfer node. This is this line, the first line of that deferred coroutine. So now we invoke it, because this coroutine returned from process backwards of the target node is now awaiting for propagate backwards actions, and that action is this deferred coroutine. So we execute this line. We can see this in the log here. We acquire the lock. We can see that we acquired the read lock on the input pin of the transfer node. So we acquire the lock on the input pin of the transfer node, and we call propagate backwards, which will find the connected pin, which is the output pin of the source node, and will get the owning node, which is the source node, and tell it to process backwards. And we can see it in this line of the log file. The process backwards of the source node is called under this lock we acquired, this lock here. We can see that process backwards of the source node returns a deferred end, a no action. It's not a coroutine, it's just no action. And then we unlock the input pin of the transfer node. So once this line ends, we unlock this lock, and we co-await on the action returned to us by the source node. But this action is deferred end. So the child action of this coroutine is that deferred end, which is no action. This condition will be met when we call next on the promise of that coroutine we're awaiting in. There's no action. So this co-await will just come back here. This will do nothing. There's no action. Just this line of code will say false. So we end up here straight away. So the next line in the log file should be receive data, which is the case. Receive data requires to log two pins. Receive data requires to log the input pin of the transfer node and the output pin of the source node, because we need to read from this output pin into this input pin. So both pins need to be locked for that moment. We can see it here. Both pins are locked, and the data is received in between those two lines in the log. We don't log that. So we call receive data here. We log the input pin for writing, and we call on that input pin receive data, an input pin will lock connected pin, which is the output pin, for reading. This pin is an output pin. So we lock the input pin for writing, we get the connected pin, and we lock this pin for reading, and we get data from that pin, the data from this pin, and we call set data on our input pin here. And after this line, we release this lock and we return. So this is our received data. And next we return this data and pass it as an argument to the function of our transform. So this is the part where we receive the data. We lock the input pin of the transform node for writing, and we lock the output pin of the source node for reading. So that's what we're seeing. The next step is to set the data. It's this line here. We lock the output pin of the transform node. We lock the output pin of this transfer node. And we just call set data on it with the result. We just set the data here. And after this, the coroutine finishes. So we lock the output pin of the transfer node and we set the data on it. So this is the next step that happens in the deferred coroutine returned by process backwards from the target node. So we have 2 locks and 2 unlocks. And this is this line. We're locking the input pin of the target node, this pin here, and we receive the data onto that pin, which, as we remember, will lock the connected pin for reading. This one is the connected pin. It's an output pin of the transfer node. It now has this new data, so we lock it. We get the data from that pin, this data, and we set it on our pin. So this is what happens in this block here. So we set it. And now, this is it. This is the execution of the deferred coroutine tracked down in the log file. This coroutine here that we return from process backwards method of the target node. And next, we have the second one, the second target node. And this is the execution of the coroutine returned by the process backwards of the second target node. It's the same. We will see the same thing in parallel version. So this is a parallel version. However, in the parallel version, the logs will interleave from 2 different threads. So you can see there's a monkey and beaver, 2 threads, and those logs are interleaving. You can see that the process backwards on monkey thread started a little bit earlier than the one on beaver. This is the latency introduced by using the second thread. Alright, so we have these wonderful coroutines as our deferred actions now. In this episode, we have learned how we can turn coroutines into deferred actions and execute them in a way that allows us to reduce the amount of simultaneous locks acquired. And it helps preventing some deadlocks. If you always execute graph in one direction, like backwards or forwards, for example. And of course, we have parallelism. So those coroutines, they're sequential. They stay on the same thread as they started, but you can run them on multiple threads. So if you have 2 deferred coroutines, they can run on 2 threads. Yeah, so that's our asynchronous NodeGraph execution on both parallel threads and with help of coroutines. And yeah, comment, like, subscribe, and stay tuned for more videos.